Today we are going to correct our Christmas worksheet. So let's start with exercise number 1. On the label of a commercial hydrochloric acid solution, denoted by capital letter S0, containing the two ions H plus and Cl minus, we read the following information. Density, it's equal to 1.18 gram per mole, percentage by mass 31%, and you have the molar mass for hydrochloric acid 36.5 gram per mole. Question number 1. Show that the molar concentration of the commercial solution is around 10 mole per liter. So you will use the only relation percentage by mass equal mass of solute divided by mass of solution times 100. So here instead of mass of solute we write number of mole times molar mass. Instead of the mass for solution we write density times V. So you will get that the percentage by mass it's equal to the molar concentration times molar mass over density times 100. So we can deduce that the concentration for this solution it's equal to 10 mole per liter. But here don't forget to convert the density from gram per milliliter to gram per liter by multiplying with 1000. So it's proved. Question number 2. The commercial solution is diluted X times to obtain 500 ml of solution A of molar concentration 0.1 mole per liter. So here you have the molar concentration for the diluted solution 2.1. Determine the dilution factor X. Here upon dilution number of moles of solute is conserved, so we can say that number of mole before dilution it's equal to the number of mole after dilution. Since number of mole it's equal to concentration times the volume for the solution, so we can write that C0 times V0 coming from the initial solution equals C prime times V prime for the diluted solution. So now we can write the following relation. C0 over C prime it's equal V prime over V0 it's equal to X, the dilution factor. So here in this question, since you have the molar concentration for the diluted solution and you have the molar concentration for the initial concentrated solution, so we can say that C0 over C prime it's equal to 10 over 0.1 mole per liter, it's equal to 100 times, which is X. Now question 2.2. Explain the experimental procedure to be followed for the preparation of the diluted solution. Before writing the procedure, first of all you have to calculate V0, the initial volume. So again, using the same relation, here V prime over V0 it's equal to the dilution factor X, it's equal to 100 times. V prime it's equal to 500 milliliter, so we can say that V0 equal V prime over the dilution factor it's equal to 5 milliliter. Now we are going to write the procedure. Step number 1. Using 5 milliliter volumetric pipette, withdraw 5 milliliter of the commercial solution of hydrochloric acid. Step number 2. Introduce them into a volumetric flask of capacity 500 milliliter, half filled with water. Now add distilled water to the line mark, then close the flask and shake it well to homogenize the solution. Now question number 3. A certain volume V of the diluted solution A of molar concentration 0.1 mole per liter, don't forget that, it is added over a metallic mixture that consists of silver Ag, iron Fe and zinc Zn. Here in this exercise, reactants are in stoichiometric proportions and the number of moles of Fe2 plus formed at the end of the reaction is equal to 3 times 10 to the power minus 3 mole. Also, at the end of the reaction, the obtained mixture is subjected to filtration and the remaining residue is of mass 1.17 gram. So, question 3.1, write the equations of the reaction that took place. Here, looking at the given information at the classification here, we can say that the acidic solution, which contains H plus ions, it will react with iron, Fe, and zinc metal only, since Fe and zinc have more reducing power than H2, and silver Ag will be collected as a residue. So let's start with the first equation. Here we have a reaction between H plus and Fe. So according to gamma rule, a reaction took place between the stronger oxidizing agent H plus and the stronger reducing agent Fe. So the unbalanced equation will be H plus plus Fe. It will give Fe2 plus hydrogen gas H2. Now let's balance it by adding the electrons. We have 2H plus 2 electron. It will give H2. This is the reduction half reaction, the one who undergoes H plus is the oxidizing agent, so it's the one who undergoes reduction half reaction. The second equation, half reaction, we have Fe gives Fe2 plus 2 electrons, so this is the oxidation half reaction. By removing the 2 electrons, the overall balance equation will be 2H plus Fe. It will give Fe2 plus H2. This is equation number 1. Now moving for the second equation, also there is a reaction between H plus and zinc. So here, according to gamma rule, again a reaction took place between the stronger oxidizing agent H plus and the stronger reducing agent zinc. So the unbalanced equation will be H plus zinc. It will give zinc ion plus H2. So the same steps, balancing the two half reactions. So we can deduce that the overall balance equation will be 2H plus zinc. It will give Zn2 plus H2. So this is the second equation, equation 2. Now question 3.2 gives the redox couples involved in the reaction. So the involved redox couples are H plus H2 coming from the acidic solution, Fe2 plus Fe, and you have Zn2 plus /Zn. Now question 3.3, identify the residue collected on the filter paper. Silver metal Ag will not react with the acidic solution since Ag has less reducing power than H2, so Ag metal will be collected as a residue on the filter paper. Now 3.4, determine the mass of iron Fe in the metallic mixture. Here, according to the given information, reactants are in stoichiometric proportions and the number of moles of Fe2 plus formed at the end of the reaction is equal to 3 times 10 to the power minus 3 moles. So it's very important information here. So depending on equation 1, the reaction between the acidic solution and the iron, we can say that according to the stoichiometric ratio of the reaction, the number of mole for H plus reacted over the coefficient 2, it's equal to the number of mole for iron reacted over 1. It's equal to the number of mole for Fe2 plus formed over 1. It's equal in return to the number of mole for hydrogen H2 over 1 formed. So here from this stoichiometric ratios, we just took the ratio for iron Fe and the ratio for its ion Fe2 plus. So the number of mole for Fe reacted over 1 equal number of mole for Fe2 plus formed over 1. It's equal to the given information here. It's 3 times 10 to the power minus 3 mole. So here you have the number of mole for iron which is reacted. We can say that an equal mass over molar mass. So directly you can deduce that the mass for iron, it's equal to 0.168 gram. Now question 3.5, determine the mass of zinc present in the alloy knowing that the number of moles of Fe reacted is a triple that of zinc. So we can say that the number of mole for iron reacted equal to 3 times the number of mole for zinc which is reacted. So we can deduce that the number of mole for zinc, it's equal to 10 to the power minus 3 mole. So the number of mole is equal to mass over molar mass. So we can deduce directly that the mass for zinc it's equal to the number of mole times its molar mass, 65 gram per mole. So it's equal to 0.065 gram. Now 3.6, deduce the mass of the metallic mixture. So according to the given information, they told us that at the end of the reaction, the obtained mixture is subjected to filtration and the remaining residue is of mass 1.17 gram. So this mass represents the residue, which is the mass of silver. You have the mass for zinc, you calculate it, it's equal to 0.065 gram, and you have the mass for iron, it's equal to 0.168 gram. So we can say that the total mass for the metallic mixture is the total mass for zinc, iron and silver. So by adding these three values, you will get the total mass for the metallic mixture is equal to 1.403 gram. Now 3.7, calculate the total volume of hydrogen gas released at the end of the reaction. Here you will notice that we have two reactions, and from the two reactions we have the release of hydrogen gas. So you need to calculate the amount of hydrogen released from the first equation and the amount of hydrogen gas released from the second equation, and I'm gonna add them together in order to calculate the volume of hydrogen gas. So let's start with the first reaction, the reaction between iron and the acidic solution. According to the stoichiometric ratio, number of mole for iron over 1 reacted equal the number of mole for the released hydrogen gas over 1, which is formed. So you have the number of mole for iron is equal to 3 times 10 to the power minus 3 mole, so it will be equal to the number of mole for hydrogen gas formed only from reaction 1. So we will use this relation N equal V على V molar. So we can say that the volume for hydrogen gas is equal to the number of mole times the molar volume, which is equal to 24. So the volume for hydrogen gas released only from the first reaction is equal to 0.072 liter. Now moving to the second reaction, here the reaction occurred between the acidic solution and zinc metal. According to stoichiometric ratio, the number of mole for zinc reacted over 1 is equal to the number of mole for the released hydrogen gas, which is formed at the end of the reaction. So we can say that the number of mole for hydrogen gas is equal to 10 to the power minus 3 mole. The same relation, number of mole is equal to the volume for this gas divided by its molar volume. So you can deduce that the volume for hydrogen gas released from the second reaction is equal to 0.024 liter. So here in this question, I need to calculate the total volume of hydrogen gas released. So I'm gonna add the two values. So the total volume for hydrogen gas is equal to 0.072 liter plus 0.024 liter. It's equal to 0.096 liter. Now 3.8, determine V. A certain volume of the diluted solution is added over a metallic mixture that consists of silver, iron and zinc, and they told us that reactants are in stoichiometric proportions. Now V represent the volume for the acidic solution, so I'm gonna calculate the volume for the H plus. The same, we will depend on both reactions. We will start with the first reaction. Here we have the reaction between iron and the acidic solution. According to stoichiometric ratio, the number of mole for H plus over 2, which is reacted, it's equal to the number of mole for iron reacted over 1. So we can say that the number of mole for the H plus ions reacted, it's equal to 6 times 10 to the power minus 3 mole. Now going to the second reaction, reaction 2. Here's the reaction between the acidic solution and zinc. According to the stoichiometric ratio, number of mole for the H plus ion over 2 reacted equal to the number of mole for zinc reacted over 1. So here we can deduce also that the number of mole for H plus ion, which is reacted only in reaction 2, it's equal to 2 times 10 to the power minus 3 mole. So here I'm gonna add the number of mole, the total number of mole for H plus ions present in solution A and reacting in reaction 1 and reaction 2, it's equal to 6 times 10 to the power minus 3 mole, which is reacted in reaction 1, plus 2 times 10 to the power minus 3 mole, which react in reaction 2. It's equal to 8 times 10 to the power minus 3 mole. So here till now we calculate the total number of mole for H plus ions present in solution A, in the diluted solution. Now I need to calculate the volume for this solution, and don't forget that you have the molar concentration for the diluted solution. It's equal to 0.1 mole per liter. It's given for you. So here the concentration, the molar concentration, is equal to the number of mole, the total number of mole for H plus ions divided by the volume for this solution, and you will get that the volume of this solution is equal to the number of mole over the molar concentration. It will be equal to 0.08 liter. So capital letter V, it's equal to 0.08 liter, or we can say that it's equal to 80 milliliter. Now let's move to exercise number 2 about galvanic cell. Here in this exercise, it is required to construct a lead copper galvanic cell using potassium nitrate solution in the salt bridge. When the cell starts function, it is noted that the electrons flow from the electrode A to the electrode C. Now question number 1, label the adjacent setup. A is the PB electrode, it's the lead electrode. For B, it's the Pb2 plus ions, and C, it's the copper electrode Cu. Now question number 2, based on the text, identify the anode of the cell. When the cell starts function, it is noticed that the electrons flow from electrode A to electrode C, so from lead electrode to the copper electrode to Cu electrode. So we can say that lead electrode is the anode. Now question number 3, write the anode half reaction, cathode half reaction, and the overall reaction. You have to know that always anode is where the oxidation half reaction takes place. So we can say that anode half reaction, it will be Pb changing into Pb2 plus into the ion, and we have plus 2 electron after the arrow. Now for the cathode, cathode is where the reduction half reaction takes place. So the cathode half reaction will be Cu2 plus ion plus 2 electron. It will give and change into the copper metal Cu. So by adding these two half reactions, we will get the overall balance equation, where Pb, it will react to Cu2 plus to give Pb2 plus plus Cu. Now question number 4, indicate how does the concentration of Cu2 plus vary when the cell starts functioning. So when the cell starts functioning, the concentration of Cu2 plus decreases with time, since it is a reactant, and it will disappear and transform into copper metal Cu. So the concentration, it will decrease with time. Now question 5, calculate the electromotive force of the cell. The electromotive force of the cell, it's equal to the standard potential of the cathode minus the standard potential at the anode. So here we can say that we have the standard potential at the cathode, which is for Cu2 plus Cu, minus the standard potential at the anode, which is for Pb2 plus Pb, and these two values, they are given for you. So we can say that we have 0.35 volt plus 0.13 volt, so the electromotive force of the cell, it will be equal to 0.48 volt. Now number 6, give the cell notation of the cell. It will be written as the following. We have here the anode. At the anode we have Pb changing into Pb2 plus, salt bridge in the middle, and at the cathode we have Cu2 plus changing into Cu, and we put here plus for the cathode. Now question number 7, the electrode at anode has a mass of 10 gram. It is dipped into 150 milliliter of solution of 0.01 mole per liter of its metallic ion. So at instant t, at a certain instant, the mass of the electrode at the anode, it will become 8.7 gram, decrease in mass. So here this electrode reacted and decreased in mass. Given the molar mass in gram per mole for lead, it's equal to 107 gram per mole. Now 7.1, calculate the change in mass of the electrode at anode at instant t. So here we can say that the change in mass, it's equal to the initial mass for lead minus the left mass at instant t. So we have 10 gram minus 8.7 gram. So the change in mass is equal to 1.3 gram. Now 7.2, reduce the number of moles of the metallic ion formed at anode at this instant. So here I need to calculate the number of mole for the Pb2 plus formed at the anode. Now from the change in mass, we can deduce that this value represents the mass of lead reacted at instant t, which is 1.3 gram. So by calculating here the number of mole for a lead which is reacted is equal to 1.3 divided by its molar mass. So we can say that the number of mole for lead reacted at this instant is equal to 6.28 times 10 to the power minus 3 mole. So at the anode half reaction, we have Pb changing into Pb2 plus and losing 2 electrons. So here we can say that according to the stoichiometric ratio, the number of mole for lead reacted over 1 is equal to the number of mole for Pb2 plus formed over 1. I need to calculate this value, the number of mole for Pb2 plus. So it will be equal to 6.28 times 10 to the power minus 3 mole. Now 7.3, calculate the total number of moles of the metallic ion, which is Pb2 plus, obtained at the anode at the same instant. So here we will need to calculate the number of mole for Pb2 plus, which is the total number of mole at the anode. So depending on the initial information, they told us that the electrode at anode has a mass of 10 gram and it is dipped into 150 milliliter of solution of 0.01 mole per liter of its metallic ion Pb2 plus. So here we can calculate the initial number of moles for Pb2 plus which are initially present in the solution after starting the chemical reaction. So here you can say that the number of mole is equal to the molar concentration times the volume for the solution. So it's equal to 0.01 times 250 milliliter. Don't forget to change from milliliter to liter by multiplying with 10 to the power minus 3. So you find that the number of mole for Pb2 plus initially present is equal to 2.5 times 10 to the power minus 3 mole. So here I need to calculate the total number of moles for the metallic ion Pb2 plus. So the total number of moles is equal to the initial number calculated here plus the number of moles for Pb2 plus formed, which is calculated in the previous question. So we can say that the total number for lead Pb2 plus ion, it's equal to 8.78 times 10 to the power minus 3 mole. Now 7.4, determine the new concentration of the metallic ions at the anode at this instant. So the concentration, the new concentration is equal to the number of mole divided by the volume of solution. But here I'm gonna use the total number of mole, since I will calculate the new concentration. So we can say that we have 8.78 times 10 to the power minus 3 mole divided by the volume for the solution. The only volume 250 milliliter times 10 to the power minus 3. So you will find that the new concentration will be 0.035 mole per liter. So the concentration increase. So we can say that the concentration of the metallic ions Pb2 plus at the anode increases when the cell starts functioning. Now moving to exercise number 3. Referring to the electrochemical classification of the redox couples given below, write the balanced equation of the redox reaction occurring between the couples Fe2 plus Fe and Al3 plus Al. According to gamma rule, a reaction took place between the stronger oxidizing agent Fe2 plus and the stronger reducing agent Al. So here we have a reaction between Fe2 plus Al to give Al3 plus Fe. So here the reduction half reaction will be Fe2 plus 2 electron giving Fe. The oxidation half reaction we have Al gives Al3 plus 3 electron. And here by multiplying the reduction half reaction with 3 and multiplying the oxidation half reaction with 2, you will get the overall balance equation where we have 3 Fe2 plus 2 Al. It will give 3 Fe plus 2 Al3 plus. Now identify the reducing agent. Al is the reducing agent since it is oxidized undergoing oxidation. Part C, give by justifying your answer the color of the obtained solution. Given for you the color of Fe2 plus ions, it's green, and Al3 plus is colorless. So here the color of the solution changed from green to colorless due to the disappearance of Fe2 plus and the formation of Al3 plus. Now question number 2. Au3 plus ions are reduced by hydrogen gas into Au. Translate the above statement into two half reactions. Here we can say that Au3 plus changes into Au, so it will gain 3 electrons to become Au. This is the reduction half reaction. And we have H2 gives 2H plus 2 electron. This is the oxidation half reaction. Now part B, deduce the overall reaction. We will multiply the first reduction half reaction with 2 and multiply the oxidation half reaction with 3. So you will obtain the overall balanced equation. We have 2Au3 plus 3H2 which give 6H plus 2Au. Now question number 3. A lead strip is dipped into 2 beakers containing H plus and Fe2 plus solutions. A redox reaction takes place in beaker A while in beaker B nothing is observed. Now rewrite the electrochemical classification of the redox couples on your answer sheet and then identify the position of the P2 plus Pb couple in the classification. So here in beaker A, we can say that Pb is more reducing agent than H2. So Pb2 plus Pb couple will be placed below the H plus H2 couple in the classification. In beaker B, since there is no reaction here in this beaker, we can say that Fe is more reducing agent than Pb. So here Pb2 plus Pb will be placed above Fe2 plus Fe in the classification. So here we can say that this couple Pb2 plus Pb will be in the middle between H plus H2 and Fe2 plus Fe. Please be safe and keep up the good work. Thanks for watching.